Assalamualaikum and a very good day to our lecturer and friends. Today we are presenting our design for 4-bit arithmetic logic unit or ALU. In modern computing, RISC/V has become the industry standard for open source low power embedded systems. The ALU is essentially the heart of the RISC-V CPU. It is responsible for every mathematical calculation and logical decision the processor makes. For this project, we didn't just aim for a working circuit. We followed a strict modular design philosophy. Our goal was to optimize the hardware by using the least number of logic gates possible. We achieved this by implementing logic sharing and multifunctional units, which we will explain as we walk through our 7-step design process. So step 1 was the foundation, the gate level 1 bit full adder. To verify this, we use a synchronized clock method in our simulation. By giving A, B, and C in different clock periods, we generated all possible binary combinations from 000 to 111. If you look at the waveform, you can see that when all three inputs are high at 140 ns mark, the sum and carry out both go high. This successfully proves the truth table logic 1 plus 1 plus 1 equals 3, which is 1 1 in binary. This perfect result allows us to move to the 4-bit stage with total confidence. Okay, so in step 2, we built a 4-bit arithmetic unit. Our optimization here is the 2-in-1 layout. We use XOR gates as controlled inverters to perform both addition and subtraction in one chain of adders. In the simulation, we use a fixed test case of 7 and 3. For the first 480 ns, we set C in to 0. The ALU is in addition mode, and you can see the output is 1010, which is 10. Correct. After 480 ns, we flip C in to 1. The XOR gates perform a bitwise inversion of B, and the initial carry in adds 1. This performs 2's complement subtraction, and the output immediately changes to 0100, which is 4. This proves our least gate arithmetic logic unit is 100% accurate. For the logic unit in step 3, we implemented bitwise XOR and XNOR. To minimize gates, we shared the XOR output and simply inverted it with a NOT gate to get the XNOR result. To verify this, we set input A to 1010 and B to 1100. In the waveform, notice how bit 3, where both inputs are 1, show an XOR result of 0 and an XNOR result of 1. This bit by bit check confirms that XOR is high only when inputs differ, and XNOR is high only when they are the same. The mirror image waves in our simulation prove the sharing method works perfectly. Step 4 and 5 involve the multiplexer, which is the selector of the ALU. We built a 4-bit 4x1 mux by ganging 4 1-bit muxes together. Okay, this is the result of combining all 4 muxes together. This is the schematic diagram. Okay, this is our waveform output for the front layer of the 4-bit mux. And this is the waveform output for our back layer 4-bit mux. In our simulation, we gave each of the 4 inputs a unique 4-bit constant. As we cycled the select lines from 00 to 11, the output Y successfully picked and displayed each source in order. This verified that our data path routing is correct and there is no cross wires between the bit positions. Okay, I would like to add on something. This is our schematic diagram for our back layer 4-bit mux. And this is the 4-bit D flip-flop that will be implemented in our final logic circuit. Okay, finally, we integrated all modules into the Figure 2 architecture. For our final verification, we did an in-depth system test. Okay, so this is the waveform output for our final ALU design. Uh, there are a few conditions which when A selector is equal to 0, 0, V selector is equal to 0, 0, and when the ALU selector is equals to 0, 0 at 0 to 100 ns, 0, 1 from 100 to 200 ns, 1, 0 from 200 to 300 ns, 11 1, 1 from 300 to 400 ns, and when A0 is set to 3, which is 0, 0, 1, 1 in binary form, and V0 is set to 1, which is 1, 0, 0, 0, 1 at binary form. Okay, so this is the upper waveform for the other condition. As we set A selector to 0, 1, B selector to 1, 0, and when ALU selector is equal to 0, 0 from 0 to 100 ns, 0, 1 from 100 to 200 ns, 1, 0 from 200 to 300 ns, 1, 1 from 300 to 400 ns, and when A1 is set to 3, which is 0, 0, 1, 1 in binary form, and B2 is set to 1, which is 0, 0, 0, 1 in binary form. So in conclusion, we have designed a fully functional gate-optimized ALU. By following these modular steps and verifying every transition, we ensure a design that is robust, efficient, and meets all project specifications. That's all from now. Thank you for your time, lecturer.